Hello students, welcome to this video lecture on surface tension, which is given as section 10.6 of chapter number 10 on mechanical properties of fluids. You must have noticed that oil and water do not mix. Water wets us but not ducks. Mercury does not wet glass but water sticks to it. Oil rises up a cotton wick in spite of gravity. Sap and water rise up to the top of the leaves of the tree. Hair of a paintbrush do not cling together when dry and even when dipped in water, but form a fine tip when taken out of it. All these and many other such experiences are related with free surfaces of liquids. As liquids have no definite shape but have a definite volume, they acquire a free surface when poured in a container. These surfaces possess some additional energy. This phenomenon is known as surface tension and it is concerned with only liquids. Please note, it is concerned with only liquids as gases do not have free surfaces. Let us understand this phenomenon in this part 3 of our video on mechanical properties of fluid. I welcome you once again. Surface tension. Surface tension is a force per unit length, or it is surface energy per unit area acting in the plane of the interface between plane of the liquid and any other substance. It is also the extra energy that the molecules at the interface have as compared to the molecules in the interior. That is, the molecules at the surface have a different energy, extra energy as compared to the molecules in the interior part of the liquid in a container. By definition, surface tension represented by capital letter S equals F by L. F is force and L is the length, where F is the force acting on either side of the imaginary line on surface and L equals length of the line. The SI unit of surface tension is newtons per meter. The dimensions of S are within brackets S equals m into t to the power of minus 2. Factors affecting the surface tension are: the surface tension decreases with increase in temperature. So if we increase the temperature, the surface tension decreases. Similarly, soluble impurities increase the surface tension, whereas sparingly soluble impurities decrease the surface tension. Now we will further define a term called surface energy, which is represented by symbol capital E. The molecules on the surface experience a net downward force, so to bring a molecule from interior to the free surface of the molecule, the amount of work done against the internal forces get stored as extra potential energy of the surface molecule, and this is called surface energy. The SI unit of surface energy E is J, that is joules, and dimensions of E are within big bracket E equals ml square t to the power of minus 2. Now we will derive the relation between surface tension and surface energy. Please refer the figure shown on the screen. As we have discussed that an extra energy is associated with the surface of liquid. The creation of more surface, that is the spreading surface, keeping other things like volume fixed requires additional energy. To appreciate this, consider a horizontal liquid film ending in bar free to slide over the parallel guides as shown in the figure. This is the bar which is free to move inside a fluid. The figure A shows a film in equilibrium and figure B shows the film stretched an extra distance. Here, when you stretch the bar, it is stretched to an extra length d as shown in the figure. Suppose that we move the bar by a small distance d as shown above, and since the area of the surface increases, the system now has more energy. This means that some work has been done against an internal force. Let this internal force be F vector F. The work done by the applied force is given by the relation force into distance F into d, that is equal to Ft. From the conservation of energy, this is stored as an additional energy. If the surface energy of the film is S per unit area, the extra area is 2 into dl. That is because the film has two sides and the liquid in between. So there are two surfaces and extra energy is S into 2d into L. That is equal to Fd. Let it be equation 1. Therefore, simplifying the equation 1, we get S is equal to Ft by 2d into L. So that becomes d and d gets cancelled, F by 2L. Let it be equation 2. This quantity S is the magnitude of surface tension. It is equal to the surface energy per unit area of the liquid interface and also equal to the force per unit length exerted by the fluid on the movable bar. Therefore, surface tension is numerically equal to increase in surface energy per unit area. A question on this section will be like this. Define surface tension and surface energy. Obtain a relation between them. This will be a 2 marks question. We have defined surface tension and surface energy in the previous slide. The relationship has been shown in this slide. Now we will study about the measurement of surface tension. Please note down the diagram, draw the diagram, and we will explain it. Surface tension can be directly measured experimentally as schematically shown in the figure above. A flat vertical glass plate below which a vessel of some liquid is kept here as shown i.e. it forms one arm of a balance. This is a balance. The plate is balanced by weights here on the right hand side shown as W. On the other side with its horizontal edge just over the water. This is water and just above the water is the plate. The vessel is raised slightly till the liquid just touches the glass plate and pulls it down a little because of the surface tension. The weights are added till the plate just clears water. Suppose the additional weight required is W. Then from equation, S is equal to F by 2L. That is, the surface tension of liquid air interface is SLA. L subscript LA equals W by 2L. W is weight is M into G, where M is the mass and G is the acceleration due to gravity and L is the length. So SLA is equal to mg by 2L. Let it be equation 3. Here m is the extra mass and L is the length of the plate edge. The subscript LA emphasizes the fact that liquid air interface tension is involved. This is how we can directly measure the surface tension. Angle of contact. When the free surface of a liquid comes in contact with a solid, it becomes curved at that place of contact. This curved surface of the liquid is called meniscus of the liquid. Angle of contact theta between a liquid and a solid is defined as the angle enclosed between tangents of the liquid surface and the solid surface inside the liquid, both tangents being drawn at the point of contact of the liquid with the solid. Please see the figure here above. The liquid is a container is filled with a liquid and the contact area is shown here. The angle in the contact area, when it is plane, it is 90 degrees, and when it is curved, it can be greater than 90 degrees or smaller than 90 degrees. In case of concave meniscus, liquid wets the solid, whereas in the case of convex meniscus, does not wet the solid surface. The value of angle of contact varies between 0 and 180 degrees. Theta equal to 0 for pure water and the glass, theta is equal to 90 degrees for water and silver. On increasing the temperature, the angle of contact decreases. Soluble impurities increases the angle of contact. The partially soluble impurities decreases the angle of contact. Then there is another term called excess pressure. A change in pressure occurs when the free curved surface of any liquid changes. The difference in pressure occurs between the inner side of the surface and the outer side of the surface. This results in excess pressure. We will further explain excess pressure in our next slide. Drops and bubbles. One consequence of surface tension is that free liquid drops and bubbles are spherical if effects of gravity can be neglected. We have seen on several occasions a small drop just form in a high-speed spray or a jet, or even in soap bubbles blown by children also form the drops and bubbles. In this section, we will study about three cases, that is, the liquid air interface, that is a drop shown in figure A above, and case B where liquid gas interface formed in a cavity, as well as case C, air liquid gas interface, that is double interface, air to liquid and liquid to gas interface in a drop. Let us study in detail. The consequences of surface tensions are a drop, that is shown in figure A. The pressure inside Pi of a spherical drop is more than the pressure outside the drop, PO. PO is the pressure outside, PI is the inside pressure, and the radius of the drop is r, small r. We can calculate the radius if there is a slight increase in the spherical drop radius, and if the radius increases by delta r, the extra surface energy is given by the relation 4 pi into r plus delta r whole square minus 4 pi r square into S into LA, where S suffix LA is the surface tension between liquid and air interface. That is equal to expanding and simplifying, we get 8 pi r delta r into SLA. Let it be equation 1. If the drop is in equilibrium, this energy loss is balanced by energy gain due to expansion under the pressure difference Pi minus Po. That is the pressure difference inside and outside between the bubble and outside. Therefore, the work done W is given by Pi minus Po into 4 pi r square delta r. Let it be equation 2. So that the excess pressure is Pi minus Po is equal to 2 S suffix LA divided by R. So S LA is surface tension between liquid and air. Next case is case B, where there is a liquid gas interface in a cavity. An air bubble in a liquid. This bubble is inside a liquid, would have higher pressure inside. So Pi is greater than Po. Therefore excess pressure is given by Pi minus Po is equal to 2 SAL R. That is air to liquid interface. SAL is surface tension air to air divided by R. The third case is air liquid gas interface. A bubble differs from a drop and a cavity. In this case, it has two interfaces, that is air to liquid and liquid to air or liquid to gas. Therefore, excess pressure is twice that of the normal pressure. Therefore, Pi minus Po is equal to 4 into SLG divided by R. This is the relationship. Splitting the bigger drop. When a drop of radius r, capital R, is split into n smaller drops, each of radius r, then surface area of the liquid increases. That is, r cube will be equal to n times small r cube. Capillary rise. One consequence of pressure difference across a curved liquid-air interface is well-known effect that water rises up in a narrow tube in spite of gravity. The word capilla means hair in a Latin. If the tube were hair thin, the rise would be very large. To see this, consider a vertical capillary tube of circular cross section of radius A inserted into an open vessel of water as shown in the figure. The contact angle between water and the glass is acute angle. So if the tube is very narrow, called capillary is dipped in a liquid, it is found that liquid in the capillary either ascends, that is increases, or descends or decreases relative to the surrounding liquid. This phenomena is called capillarity. The cause of capillarity is the difference in pressures on two sides sides of the curved surface of the liquid. When one end of the capillary tube of radius r is immersed into a liquid of density rho, which wets the sides of the capillary, and A is the radius of curvature of liquid meniscus. Here the angle of contact is acute. Here the angle of contact is acute as surface of water is concave. There is a pressure difference between two sides of the top surface. That is Pi minus Po. That is the inside is Pi and Po is the outside pressure, that is equal to 2S by R, that is equal to 2S by A secant theta. R is A secant theta. See, this is the expanded part of the capillary tube. So figure A is a schematic picture of a narrow and immersed water. Narrow tube immersed in water. B is the enlarged picture of near the interface here. So I will read once again. Pi minus Po is equal to 2S by R as we had derived previously. That is equal to 2S divided by A secant theta. That is from this relationship, trigonometric relationship, that is equal to 2S by A into cos theta. 1 over secant theta is cos theta, where S is the surface tension of the liquid, P is the atmospheric pressure, and height h as shown in the diagram. H is given by 2S cos theta divided by A into rho into G. The capillary rise depends on the nature of liquid and solid both. That is, it depends on the capillary rise depends on S, surface tension, density of the liquid, angle of contact theta, and the radius r. So the three cases arise out of this. Let us conclude it. If theta is less than 90 degrees, the surface contact is concave meniscus and H is positive and liquid rises in the capillary. Part 2 is if theta is greater than 90 degrees, there is a convex meniscus and H is negative and the liquid falls. Questions and answer. We will take up some worked examples to understand the concepts of the mechanical properties of fluids. First is regarding blood velocity. The flow of blood in a large artery of an anesthetized dog is diverted through a venturi meter. The wider part of the meter has a cross-sectional area equal to that of artery. That is, capital A is equal to 8 mm square. The narrower part has an area small a is equal to 4 mm square. The pressure drop in artery is 24 pascals. What is the speed of the blood in the artery? So certain quantities are given and we are required to find the speed of the blood in the artery. Let us take up the answer. The ratio of the areas is capital A by small a is equal to 2. Using the formula, we have to remember the formula for the speed of fluid at the wide neck is as V1 is equal to square root of within brackets 2 rho m gh divided by rho into a by a whole square minus 1 close the bracket to the power of minus half. This is to the power of minus half. It has to appear here. Hence, substituting the values, 2 into rho mgh is equal to 24 pascals, and the value of rho is 1060 kg meter cube into this value is 2 square minus, that is a by a is 2. 2 square minus 1 whole to the power of half, and that is also taken inside. Minus half is taken inside, and simplifying we get 0.123 meters per second. You please do it and write it step by step. Next question we will take up about an Boeing aircraft. A fully loaded Boeing aircraft has a mass of 3.3 into 10 to the power of 5 kgs. Its total wing area is 500 meters square. It is in level flight with a speed of 960 kilometers per hour. Now question is part A. Estimate the pressure difference between the lower and upper surface of the wings. Part B. Estimate the fractional increase in the speed of the air on the upper surface of the wing relative to the lower surface. The density of air is rho is equal to 1.2 kgs per meter cube. There are certain given quantities. You please write down all the given quantities and we will start answering. Answer. The weight of Boeing aircraft is balanced by the upward force due to pressure difference. We can write the pressure difference delta P into A, that is equal to 3.3 into 10 to the power of 5 kgs into 9.8. Therefore, delta P is equal to 3.3 into 10 to the power of 5 kgs into 9.8 meters per second square divided by 500 meters per meter square. That is equal to 6.5 into 10 cube newtons per square. This is the answer for part A. Next part B. Ignoring the small height difference h1 and h2 in the equation. In this equation, if we take h1 is equal to h2, both the terms on the third term on the left hand side and the third term on the right hand side get cancelled. Hence, the pressure difference delta P is given by delta P is equal to rho by 2 into V2 square minus V1 square, or simplifying and solving for V2 minus V1, we can write V2 minus V1. That is, here using the formula A plus B into A minus B and retaining A minus B on the left hand side, we get V2 minus V1 is equal to 2 into delta P divided by rho into V2 plus V1, where V2 is the speed of air over the upper surface and V1 is the speed under the bottom surface. Therefore, the average speed is given by V2 plus V1 by 2. That is equal to, that is given as 960 kilometers per second. Per hour, 960 kilometers per hour. That is equal to 267 meters per second. So, converting this kilometers into meter, that is into 1000 divided by hours. Divided hour to into second is hours into 60 into 60. We get 267 meters per second. You please solve it. That is 960 into 1000 divided by 60 into 60. You will get 267 meters per second. Therefore, V2 minus V1 divided by V average equals 2 into delta P divided by rho into V average square. That is equal to 0.08. The speed above the wing needs to be only 8% higher than that of the below. Next question. Now we will take up another word example. Question number 3. A metal block of area 0.10 meter square is connected to a 0.010 kg mass via a string that passes over an ideal pulley considered to be massless and frictionless as shown in the figure below. A liquid with a film thickness of 0.3 mm is placed between the block and the table as shown in the figure. Here the liquid is placed. When released, the block moves to the right with a constant speed of 0.085 meters per second. Find the coefficient of viscosity of the liquid. The metal block moves to the right because of the tension in the string. The tension T is equal in magnitude to the weight of the suspended mass. Thus, the shear force F is given by the relation F is equal to T is equal to mg, that is mass into acceleration due to gravity, that is equal to 0.1 kg into 9.8 meters per second square. Simplifying, we get F as 9.8 into 10 to the power of minus 2 newtons. Now, the shear stress on the fluid is F by A. So, simplifying, we get 9.8 into 10 to the power of minus 2 divided by A is 0.110 meter square. So, we get the value as shear stress is equal to 9.8 into 10 to the power minus 2 divided by 0.1 newtons per square. Therefore, strain rate is given by V by L, that is equal to 0.85, that is the constant speed, V is the velocity, 0.085 divided by 0.3 into 10 to the power of minus 3, that is equal to eta, that is stress by strain ratio. Eta is given by 9.8, substituting the values 9.8 into 10 to the power of minus 2 divided by 0.1 divided by, it gets inverted, 0.8085 meters per second, and the denominator here goes to the numerator of this equation, that is 0.3 into 10 to the power of minus 3 in meters. Simplifying, we get the answer as 3.46 into 10 to the power of minus 3 Pascal seconds. This you please write and work out yourself step by step as shown in the figure. Question number 4. The terminal velocity of a copper ball of radius 2 mm falling through a tank of oil at 20 degrees centigrade is 6.5 centimeters per second. Compute the viscosity of the oil at 20 degrees centigrade. Density of oil is 1.5 into 10 to the power of 3 kg per meter cube. Density of copper is 8.9 kg per meter cube. Let us solve it. Answer. Given V1 is equal to 6.5 into 10 to the power of minus 2 meters per second. R is equal to, radius is equal to 2 into 10 to the power of minus 3 meters. G is equal to 9.8 meters per second. Rho is equal to 8.9 into 10 to the power of 3 kg per meter cube. Sigma is equal to 1.5 into 10 to the power of 3 kg per meter cube. So we will get, therefore we will get the value as, applying the formula, Vt is equal to 2 by 9 into R square into sigma minus rho minus sigma over eta into G. I will read the formula once again. Vt is equal to 2 by 9 r square rho minus sigma divided by eta into g. This we have derived in the previous section. Substituting the values, given values, we get the answer as 9.9 into 10 to the power of minus 1 kg per meter per second. These are given in detail. You can work out yourself. Now we will take up one more worked example and then quickly glance through the very short, that is 1 mark questions. Question number 5. The lower end of the capillary tube of diameter 2 mm is dipped in 8 centimeters below the surface of water in a beaker. What is the pressure required in the tube in order to blow a hemispherical bubble at its end in water? The surface tension of water at temperature of the experiments is 7.30 into 10 to the power of minus 2 newtons per meter. 1 atmospheric pressure is equal to 1.01 into 10 to the power of 5 pascals. Density of water is 1000 kg per meter cube. And acceleration due to gravity g is equal to 9.8 meters per second square. Also calculate the excess pressure. Let us solve the problem. The excess pressure in the bubble of gas in a liquid is given by the formula 2S by R, where S is the surface tension of the liquid gas interface. Note that there is only one liquid surface in this case. The radius of the bubble is R. Now the pressure outside the bubble PO equals atmospheric pressure plus pressure due to 8 centimeters of water column. Therefore, substituting the values, we get PO is equal to 1.01 into 10 to the power of 5 pascals plus 0.08 meters into 1000 kg per meter cube into 9.8 into 9.8 meters per second square. Simplifying, we get the answer as 1.01784 into 10 to the power of 5 pascals. Therefore, the pressure inside the bubble is Pi is equal to PO plus 2S by R. That is equal to, substituting the values, we get the answer as 1.02 into 10 to the power of 5 pascals. You please solve it, write it step by step, so that you will understand very clearly. Next we will take up very short answer, that is 1 mark question. Question number 6. Why is it difficult to stop bleeding from a cut in a human body at high altitude? This is because the atmospheric pressure is low at high altitudes. Due to greater pressure difference in the blood pressure, the atmosphere pressure, that is the difference in blood pressure and atmospheric pressure, it is difficult to stop bleeding from a cut in the body. Next question. The blood pressure in a human is greater at feet than at the brain. The height of the blood column is quite large at feet than at the brain. Hence, the blood pressure at the feet is greater. This you please note. Question number 8. Define the coefficient of viscosity and write its SI unit. Definition is, it is the ratio of applied stress to the rate of straining, that is change of strain with time. So, viscosity is the ratio of applied stress to the rate of straining. And SI unit of coefficient of viscosity, please note coefficient of viscosity of liquid is kg per meter per second. Next question. Why machine parts get jammed in winter? In winter, that is at low temperature, the viscosity of lubricants increases. Why do the clouds float in the sky? Answer is, it is due to zero terminal velocity. Next question. Antiseptics have low surface tension. Why? They have to spread over large area. Hence, the value of surface tension is low in antiseptics. What will be the effect of increasing the temperature on angle of contact and surface tension? Angle of contact increases with increase in temperature while surface tension decreases with increasing temperature. Please note it. For solids with elastic modulus of rigidity, the shear force is proportional to the shear strain. On what factor does it depend on in the case of fluids? That is rate of shear strain. That is, it depends on the rate of shear strain. Question number 14. How does rise in temperature affect 1. Viscosity of affects the viscosity of gases and viscosity of liquid. What is the effect of temperature? Viscosity of gases increases while viscosity of the liquid decreases. This you please note. Question number 15. Explain why detergent should have small angle of contact. Detergents should have small angle of contact so that they have low surface tension and greater ability to wet the surface. Further, as we have tried earlier, H is equal to 2s cos theta by rho r into rho into g. That is, theta is small. Cos theta will be large. So if theta is small, by trigonometric knowledge, we know cos theta will be large. So H, that is penetration, will be high. Question number 16. Write the dimensions of coefficient of viscosity and surface tension. Coefficient of viscosity within big bracket eta is equal to m to the power of 1, L to the power of minus 1, T to the power of minus 1. Whereas the dimensions of surface tension within brackets capital S is equal to m to the power of n, 1, L to the power of minus 2 and L to the power of 0. Next question. Obtain a relation between SI units and CGS units of coefficient of viscosity. CGS unit of coefficient of viscosity eta is poise. And SI unit of eta is Poiseuille or deca poise. The difference is deca. 1 poise is equal to 1 gram per centimeter per second square. That is equal to 10 to the power of minus 1 kg per meter per second. Therefore, that is equal to 0.1 Poiseuille. Question number 18. Explain how the use of parachute helps a person jumping from an aeroplane. Viscous force on the parachute is large as F is equal to 6 pi eta into R into V. That is, F is proportional to R, so its terminal velocity becomes small. So the person hits the ground with this small velocity and does not get injured. Question number 19. Why two ships moving in parallel directions close to each other get attracted? According to Bernoulli's theorem, for horizontal flow, P plus half rho V square is constant. As the speed of water between ships is more than outside pressure between them gets reduced and the pressure outside is more. So the excess pressure pushes the ships close to each other. Therefore, they get attracted. Question number 20. Why the molecules of a liquid lying near the free surface possess extra energy? The molecules in a liquid surface have a net downward force, that is cohesion on them. So the work done on bringing them from within the body of liquid to the surface increases the surface energy. Why is it easier to wash the clothes in hot water soap solution? Answer is hot water soap solution has small surface tension, therefore can remove the dirt from the clothes by wetting them effectively. Why does mercury not wet the glass? Mercury does not wet the glass because of the larger cohesive force between mercury to mercury molecules than adhesive force between mercury to glass molecules. Why ends of glass tube become rounded on heating? When the glass is heated, it melts. The surface of this liquid tends to have a minimum area. For a given volume, the surface area is minimum for a sphere. This is why the ends of the glass tube become rounded on heating. Next question. What makes raincoats waterproof? Angle of contact between rainwater and material of the raincoat is obtuse, so the rainwater does not wet the raincoat. Question number 25. What happens when capillary tube of insufficient length is dipped in a liquid? When the capillary tube of insufficient length is dipped in a liquid, the radius of curvature of meniscus increases to that HR is equal to constant. That pressure on concave side becomes equal to the pressure exerted by the liquid column. So, liquid does not overflow. Does it matter if one uses the gauge pressure instead of absolute pressure in applying Bernoulli's equation? No, unless the atmospheric pressures at the 2 points where Bernoulli's equation is applied are significantly different. Now we will take up short answers with 2 marks. Question number 27. Figure A and B refer to the steady flow of a non-viscous liquid. Which of the two figures is incorrect and why? Please note we have to identify the incorrect and give the reasons thereof. Please see the figure. Figure A has got liquid filled up to this level, whereas figure B, this is figure B, the liquid is filled up to this point. Here it is higher and it is lower. So the reason is figure A is incorrect because the area of cross section is small. So the velocity is large. Consequently, the pressure must be small. So height of liquid must be less, as in figure B. Figure 20, question number 28. The figure below shows the thin liquid supporting a small weight 4.5 into 10 to the power of minus 2 newtons. What is the weight supported by a film of the same liquid at same temperature in figure B and C? Explain your answer. Please see the figure. A, B and C has got very different areas of contact. Though the pressure is same, that is the weight is 4.5 into 10 to the power of minus 2 newtons. So we have to get the answer. The weight supported at B and C are same as that in A. That is all the three are equal to 4.5 into 10 to the power of minus 2 newtons. The weight supported is equal to 2 into sigma into L, where sigma is the surface tension and L is the length, which is the same in all the three cases. Hence, weight supported is same. Next, now we will take up 2 mark questions and answers. Two soap bubbles, different in diameter, are in contact with certain portion common to both the bubbles. What will be the shape of common boundary as seen from inside the bubble? Support your answer with a neat diagram and justify your answer. Answer. Please draw the diagram as shown on the screen. When seen from inside the smaller bubble, the common surface will appear 2s concave as in 1, and the pressure excess will be equal to 2s divided by r. That will be greater for concave surface, and r is the small for the smaller bubble. The pressure will be greater. Next question. During the blood transfusion, the needle is inserted in a vein where gauge pressure is Pg. P suffix G is the gauge pressure and the atmospheric pressure is P. At what height must the blood container be placed so that the blood may just enter the vein? Given density of blood is P. Density of blood is rho. Density of blood is rho. Therefore, Pg is equal to rho GH. That is, H is equal to Pg divided by rho into G. Why we can't remove a filter paper from a funnel by blowing the air to the narrow end? The diagram is shown on the screen. When air is blown through the narrow end, that is this end, its velocity in the region between filter paper and glass increases. This decreases the pressure. The filter paper gets more firmly held with the wall of the tunnel. Question number 32. On a hot day, a car is left in sunlight with all windows closed. Explain why it is considerably warmer than outside after some time. The glass transmits 50% of the heat radiation coming from the hot source like sun, but does not allow the radiation from the moderately hot bodies to pass through it. Question number 33. A capillary tube is dipped first in cold water and then in hot water. Comment on the capillary rise in the second case. Answer. We know that H is equal to 2s cos theta divided by R into rho into G. Surface tension of hot water is less than the surface tension of the cold water. Moreover, due to thermal expansion of the radius of the capillary tube will increase in hot water. Due to both the reasons, the height of capillary rise will be less in hot water as compared to the cold water. This we come to the conclusion of mechanical properties of matter, that is chapter number 10. Our next lecture will be on thermal properties of matter part 1. Till then, goodbye.